It's now my pleasure to introduce our next speaker, Marten Scheffer, who is one of the leaders, and some would argue one of the progenitors of the field of asking questions about the possibility of early warning signals in complex systems. We're delighted Marten can be here today, and I need to poke a little fun at him on the way in. Not all of our speakers are quite as adept at publicity and public relations as Marten apparently is. He arranged for this article to be published in the major scientific journal in the US and the rest of the world, Science. Today, I won't take credit on behalf of the Institute for saying that he really intended this, but it's a great honor to be able to show this profile, and I think it's quite an appropriate profile, and would recommend it to all of you. Marten's colleague Tim Linton, who is going to be speaking to us later, is quoted in the article, as are Simon Levin and others known to this community. So with that little bit of both respect and humor, Marten.
So that's the CO2 molecule. So one of the things, if you get to the university, you study science, you're impressed by all the things that are known. We know so much about so many things that you're overwhelmed, and you think it will be very hard to come up with something new when you're a student. But if you think about what we know about, really, we know mostly about the easy stuff, the small things. We know about the CO2 molecule, how it works, but asking what happens if you put more of those CO2 molecules in the atmosphere of the Earth is much more difficult to answer. Like in ecology, we know of all kinds of fishes, how quickly they can swim, how many eggs they produce, and all that quite accurately. But then if you put those in a complex system, and you want to know what is the resilience, the response, the change in coral reefs, that becomes much more difficult. We know all kinds of things about humans in psychological tests, and when you get fever and all kinds of things, but when you add them up in society, it's very hard for us to understand why at some point suddenly you get changes in society, changes in points of view, changes in the Arab world, wherever. We find it very difficult to understand those complex systems. So I'm fascinated by trying to understand a bit of that complexity, and really a key word in understanding that what I'm concerned with is resilience. So resilience is, of course, a word that everybody knows, and it's basically you find it everywhere. This is a cream called Resilience Lift Extreme. So it's very good for your skin. Whatever challenges your skin, it'll bounce back into shape. So that's resilience, and we understand that as the capacity to, upon some challenge, upon some shock, to actually recover. But that's only one way of looking at resilience, because if you pull the skin too much, maybe it'll break, or it'll never recover. And there's many changes in complex systems that, if they're challenged, they don't recover to the same state. Like the Arab Spring may have been triggered by a rise in the price of the bread, which was triggered by the high prices of wheat, which were the result of a drought in Russia. So it put a stress on the system, and then the bread prices returned, but the system didn't return. It actually moved on to a very different state, and that's so. It's one thing to ask how much of a or how quickly will you return, that's resilience. Another thing is, will you return at all to the previous state, or will you slip into something qualitatively different? Now, that is something that Bob May has been early on talking about, an influential review in Nature, and alternative stable states, the possibility of that in systems. And more or less at the same time, Buzz Holling, C.S. Holling, was working on those ideas and wondering how you could reinterpret resilience, not in terms of just the capacity to bounce back, but also, okay, how much stress can a system take before it actually does not return back? It goes to something very different. Now, I've been starting to study all this in lakes. I grew up as a young student reading the stuff of Bob May and being inspired by the magic of thinking in a mathematical way about systems. But my first job was a very applied one. It was in lake ecology. We had to try to clear up lakes that became murky, and actually we found that the reason for that was an overload with phosphorus and nitrogen and like pollution of the lakes. And then we would reduce that stress, but the lakes would never come back. They stayed murky. And then we gave them a shock therapy, taking out fish temporarily, and they would become clear again. And then we realized they could slip into either of those two states, clear or turbid, and be kept in those. So those were alternative stable states. And that's one thing to think about. And you can imagine there is this self-amplifying mechanisms that once a lake is clear, it will keep the lake clear, and vice versa. But it's not so easy to think about what can make one of the states gradually fragile. So the easiest way is an experiment, and I'll tip over a chair for you. I'll put it a bit higher because I noticed that actually it's a bit low to. So let's do it this way. So as you know the chair and you know the idea of the tipping point, so you know that if you know somebody is sitting on the chair and maybe you've experienced it yourself and you're leaning back too far, you get to this particular point and it's the tipping point. But what is interesting at the tipping point is if I put more stress on the system, at some point, if a fly shits on this chair, it can go. And that's the point where this equilibrium has become really fragile. At that point you may say, well, this fly tipped over my chair and we shouldn't allow chairs in this building anymore, flies in this building anymore because they tip over chairs. But of course it's not about that, it's about what happened before. And what happened before for the chair is easy to see. It's not so easy to see for a complex system. What makes a system fragile to the point that even a little event can actually flip it into some self-propagating change towards another state? So that's a question that we've been studying in lakes. And again, the theory of all that is old. And even before Bob May and Buzz Holling studied it, it was a fascination of Salvador Dali that had read and heard of the work of a mathematician in France, René Thom. That was the so-called catastrophe theory, which was all about those transitions in systems. And it is the last painting made by Salvador Dali, and it's the last picture taken from him. After that, he went through his final tipping point. He died, and he was, I think it's a statement that he intuitively felt this was about really important things in life that captured some essence. So then as you see this shape, it's the same shape here that in, I think, 2001, we were still able to publish a paper on that in Nature, even though Salvador Dalí was already painting it much earlier. So what was new was that actually over the time we've been better able to actually tie this whole concept not just to tipping chairs or boats or so, but to ecosystems and later to other systems in the laboratory and in the field. So what you see here is the equivalent of the tipping chair. Here is the stress you put on the system, and there is two stable states. The ball can be in any of those two stable states, and what can happen is that the landscape around the ball is changing in such a way that in the end it's sitting in a very tiny place, so whatever pushes the ball, it may actually flip over. Now this is always behind it is some like self-propagating feedback, that once you're out of this first equilibrium, you're propelled towards the other state with increasing speed, like the increasing speed that Bob May showed actually in the assets kept by banks as a percentage of the GDP. So implications of viewing complex systems like this are many. One is that actually you can use a little shock therapy for flipping a system from one state to the other. So that's what we did with the lakes. Of course, it doesn't make sense to try to flip this one there. You can push it, but it will roll back anyway. But if you're here, you may push it and maybe it sticks there. So depending on the stability landscape, on the underlying fragility of the two states and whether they actually exist or not, it may be possible to with a single effort, flip the system. And that can happen to lakes. It can also happen to social systems, for instance, smoking or non-smoking in restaurants. You'll see that in many places of the world the system has tipped towards non-smoking, a little enforcement by law, but then you see that people actually become very intolerant to any defector once the majority doesn't do it. So that kind of transitions have been studied. You can also think of microcredits as tipping a system. So we got a Nobel Prize awarded for that. The idea is that if a family is in a poverty trap, you may actually perturb them a little bit, give them a little bit of money, and they might flip into a more wealthy state and actually stay there. And as the committee of that Nobel Prize actually wrote, that will not always work, because if you're in a very poor country, conditions are very bad, what you're doing, actually, you're giving that credit, but sooner or later the family will slip back. So it depends on the relative stability of those alternative states. So that's one family of applications, is that you can think of flipping states, you can think of bad transitions that you don't like, or of good transitions that you would like and you would be interested in actually stimulating them. Now there are, of course, a lot of challenges involved in this, because how do you actually tie it down to reality? How do you know, for instance, whether a system is close to that tipping point? If it's a transition that you don't want, maybe you want to do something about it. If it's a transition you may want, maybe that's your chance, because there, with a little push, you can just flip it into a preferred state. So I think like perhaps the title of the previous lecture was, can we predict a critical transition? Well, we cannot. We cannot, because whether a fly sits on that chair is a stochastic kind of thing that we can never predict. There will be always things happening. There will be always droughts. There will be always people showing some risky individual actions. So the actual tipping of the chair, when that happens, you cannot predict. But what would be interesting is if you could infer how stable or how fragile a system is. Could you have some way of feeling whether you're actually close to a tipping point? So that sounds impossible. It's easy, of course, for systems that are very simple that we all know. So can we infer the fragility? That's really the question. Now for a vase, maybe you can infer it because you've seen many of those vases before. But for a situation in society, probably you've never seen the same situation before. Actually, nothing really repeats in society. For the climate, there is a lot of work on the potential of tipping points in the climate, and Tim Lenton, that will speak later, is one of the experts worldwide on that. But the climate we have now, the situation we have now on the Earth, does not have an analogy in the past. We cannot learn precisely from the past what will happen, and also we cannot really predict it with models. We have models for climate simulation. We have models for, I'm sure we have models for markets. We have great simulation models for many things, but of course nobody really trusts those models because they can tell you something, but they're so complex that it's impossible to put all the parameters in the models right. In a sense, the problem is that you can reach the same output, the same results with the same model in many different ways. You can reach the same result with many different models. Say, whenever you tune a model and you say, oh, this fits very nicely to the data, you cannot trust it because you can get the same result, the good result, for the wrong reasons very easily. So that's basically true for any complex system. It's true for the brain, it's true for the Earth, it's true for society. We don't really know how those complex systems work. So the question becomes, can we infer something about fragility? Can we know how close to a critical point we are, even if we do not know the system? So that sounds like it's impossible, and it's nearly impossible, but we have a little glimmer of hope here, and that's that there are certain universal principles in any dynamical system. And I liked very much what May is saying this morning. I have a very short span of attention because I moved from engineering to theoretical physics to ecology and now the financial system. And I think you'll find that true for most of the speakers today. Tim Lenton has been working on evolution and then on climate science, and is now interested also in economical issues. Ricard Soleil, that will speak, has moved from being interested in physics to ecology to creating synthetic life, and he'll speak to that. 2 weeks ago, I was speaking to Ken Arrow, that was memorized in the startup as one of the early people involved with Santa Fe. He was at that same meeting giving advice to a whole of young scientists in Sweden at the academy, and they were asking him, so well, if there is one advice, what would you give it? What would you tell us? And he said, well, whenever you can change your topic, do it. And he started computing how an airplane could fly best from the US to Germany. He worked on meteorology and then on many topics in economy. And maybe you saw his article just last year, I think, on discounting in Nature, that he was the first author. He is 93 years old now and going very, very strong. I like that also. a lot of the Santa Fe Institute and this meeting. We have all those generations, and I think that that's the way to go. I mean, maximize diversity, gender diversity, ethnic diversity, generational diversity, if you want to try to work together and understand those complex issues. So why I'm saying that this is related to the short span of attention. My span of attention is extremely short. I also work in ecology, then I'm studying the predictability of migraine attacks. We work on intestinal biota, climate tipping points. And I think the reason that that can work so well is that in those complex systems, you wouldn't expect it. You would think them all being very different, but actually there are universal principles, and I think that's a glimmer of hope, and it's absolutely fascinating. So in the remainder of the time I have, I'll talk you through some of that. So when it comes to the tipping points, actually there are things happening whenever a system approaches a tipping point, whether it's the brain getting closer to an epileptic seizure, or the climate to a tipping point, or a lake. And this is a picture of a workshop we had, and you will see one of those people is actually George Sugihara, that was mentioned this morning by Bob May. So we have here economists, we have climate scientists, we have physicists, mathematicians, ecologists, walking through the dunes in Holland, trying to grasp what is this universal principle that we might find, and scribbling all those overhead sheets. We published this 2009 review in Nature called Early Warning Signals for Critical Transitions, and that created a bit of a stir. This is just Nature and Science papers following that initial publication. So you see a lot of follow-up work where actually the ideas we had laid out there were demonstrated in laboratory experiments in different systems. So let me explain you briefly what the basic idea is. The idea is it's very hard to know that your stability, that you're getting close to the critical point if you just look at the state of the system. Because this ball is in the same position, right? It looks like everything is as it always was before. But something is changing. The stability landscape around the ball is changing. So can we find indicators for that? We can. If we push the ball a little bit around, if there are perturbations, you look at the non-equilibrium behavior, there may be some information in there. So specifically, if you have a nice deep well of attraction, you're stable, you're resilient, you can push but you'll fall back. It's very different from when you are almost losing your stability. Here, usually the return rate to equilibrium will be fast. The dominant eigenvalue of the Jacobian matrix, if you want, of the dynamical system is pushing you back, whereas here it's losing its power, it's becoming zero, and it becomes almost inert, and in the end the return rate to equilibrium becomes zero. And you can actually measure that by doing a little experiment. Say this is far from the tipping point, you perturb it, it's back quickly. This is close to the tipping point, you perturb it, takes longer. So that sounds like the original idea of resilience, like the capacity to return and how quickly you can return, but now it's something beyond that. It's also an indicator of a potential critical point. Now this is of course all very nice, but we cannot do those experiments everywhere. You cannot do those experiments in the global financial system. We cannot do it in the climate system. We could, but we shouldn't. So what can we then see? Can we still see it even if we cannot do this little perturbation experiment? Now the idea is, well, each system always has little perturbations. Your brain is always perturbed by little things that you see. The climate system is always perturbed by little volcano outbreaks and all kind of things. The financial system is always perturbed by national variation in productivity of crops and whatever. So systems are always pushed around. They are in a regime of stochastic perturbations, if you want. And you can show mathematically and actually understand that the result of those stochastic perturbations will start to look different as you approach a tipping point. So this is the fluctuations. This is simulations. This is the fluctuations when you're in a quite resilient state, and this is the correlation between two subsequent states. And this is when you get closer to the critical point. You see the variation increasing, but more importantly, the memory increasing. Your state next day is more like the state the previous day, or next year, previous year. Or if you look at epileptic seizures, next millisecond, previous milliseconds. So that depends on the rates, the typical rates of your system. So increased variance and increased temporal correlation. We can discuss that later, but it's quite straightforward how you can understand that happens from this dominant eigenvalue going to zero, that it happens because of this inertia coming in the system. So this idea then was tested first in realistic simulation models for the thermohaline circulation, and actually Tim Lenton, that will speak later, was one of the pioneers in this. And then it was also shown in real systems. This is our former PhD student Vasilis Dakos, that was studying abrupt change in the climate. And when you look at the history of the climate that you can reconstruct from ice cores, like many years in the back, you can make a time series. And so this is what the climate looked like. And then suddenly we got this, in this case, the end of the greenhouse Earth. Just 34 million years ago, the Earth got ice caps. That's pretty recent in geological history. This is the end of a glaciation. There was an ice cap, and suddenly, so you see, this is a property that you see a lot in the climate systems. So if you wouldn't have known, so how would you have predicted this? Well, maybe if you would have looked at the temporal autocorrelation, at this indicator of the so-called critical slowing down that happens universally in systems in many cases that approach a tipping point. Because this was building up, and then it happened. So the same here. How would you predict the future here, right? This is the future. Well, something was building up, and you could actually have measured that. Now the time scales depend very much on the particular system you're looking at. This is a time scale from 40 million years ago to 32 million years ago. So we show similar graphs in brain transitions, and they're on the scale of seconds. So that depends a lot. While you never know exactly how to understand causality in the past, so you can do things in the lab too. So we exposed a little micro ecosystem to increasing stress, and we could show that before it collapsed, just as predicted, we could see this critical slowing down. The financial system consists of a network of banks. And most of this work is on like simple single double differential equations or simple experiments. But there is, of course, this whole other field where we're interested in the robustness and resilience of networks. Bob May didn't mention it himself, but there was this beautiful article called Ecology of Bankers that was basically making the point that also for networks there is this universalities in how we understand their stability. And those universalities should apply equally well to the networks of species or to the networks of banks or of people, because they are universal principles. So we have been following up a bit to study the network of species. This is work together with Jordi Bascompte in Spain, who, by the way, is, I think, the first PhD student of Ricard Soleil. So you will speak to the teacher of Jordi later today. And our common student, Jelle Leven, who is doing his PhD with Jordi and with me. And now we put, instead of looking at the topology of networks, we put in each of the nodes of the network, we put dynamical equations and make them interact. So we were interested in this case in the network between pollinators and plants. And actually that's a facilitation, because the plant needs the pollinator needs the plant, and then the plants are competing. As George Sugihara, a student of Bob May, we have mentioned before, he wrote about some of those works, a beautiful piece, I think, in Science, where he compared this actually to the financial network of companies, where you have big companies and then you have subcontractors, and it has theoretically the same structure. And you see that very much dependent on the structure, such networks, if you put a stress on this, in this case pesticides to the system, they might either lose species every once in a while, or actually you may see very little happening until the whole system crashes as a whole. That depends on the way things are connected, and that's very much related to the thinking that has been outlined by Bob May earlier. So then this is a follow-up on understanding how the structure of networks affects their resilience. Another interesting question, of course, is whether you could perhaps see early warning signals in those networks, whether there would be any reason to expect that there could be generic things that you could see to fathom whether this network that you don't really understand, which is always the case, whether it gets close to a point of criticality. Now, if you do the models for that, and in networks there are so many things you can vary. You can vary the structure, you can vary what is in the nodes, how they affect each other. Now, when you do that, you quite universally find that when a network goes through a transition, like the one that I showed here, this is a transition, in this case very dramatically, the whole network crashes. So before that happens, you'll see this indicator of critical slowing down typically. You'll see this increased temporal correlation in fluctuations, the system moving, changing slower. But what you will also see is that for the same, mathematically the same reason, you will see a greater correlation between what the different nodes are doing. One is reacting stronger to the other, either in opposite direction or in the same direction. So that's cross correlation. And this cross correlation actually carries a lot of information that we have now, with some of the people I mentioned and some of our students, we're working on this very much, because the cross correlation pattern can actually tell you not only that you're approaching a critical point, but also where you're heading for, what might be the next situation. So that's, I think, really exciting. Now, one community that is thinking more and more in terms of networks are, believe it or not, psychologists and psychiatrists. And the networks they're thinking of are the networks, the nodes of their networks are your mood, your behavior, different elements of that. For instance, if you feel depressed, if you feel bad, maybe you don't feel like seeing other people and you're alone. But when you're alone, you feel worse. So that's a positive feedback, right? And maybe you don't feel like going out running in St. James Park. But if you don't go running in St. James Park, you just sit on your couch, you feel worse. So it's another positive feedback. And maybe you look grumpy, so nobody wants to talk to you, but when nobody talks to you, you feel worse, and you'll be looking more grumpy. So there's like this possibility, and maybe you get an eating disorder, so you get some very bad food, and that doesn't help a lot either. So these networks of issues can create traps in some people. Like there are many people that may feel bad at times, but actually bounce back. But there's also people that can become trapped, and they can end up in this major clinical depression that actually changed them entirely, and it's very difficult to get out of that again. So it's one example of a whole range of psychiatric disorders, and the current network, the current thinking of psychiatrists about that is that it's not like there is one little problem here in some part of the brain and it causes these issues. No, it's much more a network of related issues that feeds back. So when we were having a workshop with those people, and they started explaining that to us, then we said, well, that's very interesting. We have this theory that, well, maybe as you get close to a critical point, you get this increased temporal correlation and this increased cross-correlation. And if we just had data, and then some of them mentioned, well, we just got the data, because now we're having this group of 1,000 people that every hour they report different dimensions of their mood on a scale of 1 to 5. If they're anxious or not, if they're sad or not, if they're happy, if they're content. And they say, well, those issues for us are indicators of part of the mood system, and they're quite independent indicators. And they got those time series, and then we said, okay, let's look at them, because we predict that if you get an increasing cross-correlation and an increasing temporal correlation, those are indicators of critical slowing down, and we should expect that people that have that are more likely to get a depression later in life. And if you have depressed patients, if they get more autocorrelated, maybe they get closer to the tipping point for recovery. And sure enough, we looked at the data, and it worked out like that. So our graduate student Ingrid van der Leempen published this early this year in PNAS, and the data are pretty convincing that actually, yes, those are early indicators. Those are predictors for the resilience, in this case, of the mood system. So that's all about critical slowing down, which is what happens close to the equilibrium as you get to a critical point. But actually, there are more wildly oscillating systems. When then you have this so-called catastrophe fault, and you're just pushing the thing around, not just close to the equilibrium. You might end up in the other equilibrium, fall back again, and what you see, if you simulate that, is a wilder picture. You don't see any indicator of this dominant eigenvalue. Really, you're sampling the entire stability landscape. You're flipping back and forth. So that's a very different class of system. You don't see critical slowing down, but you might see indicators of what could be your potential future, because maybe here you're very briefly visiting this state and then you fall back. But actually it's the state that, if the conditions change further, it will be where you're in the future mostly. So the first explorations of that were in the climate system, and that was actually a student of Tim Lenton, who will also speak to you later today. Valerie Livina, she's working in the UK now, and she figured that actually from the dynamics of the system you could figure out what should be the underlying stability landscape of the bulls and the cubs. So we thought that was really smart, but we didn't have the data. But in mathematics, whether something is space or time doesn't matter, you can interchange them. So we started looking at satellite images of the tropical rainforest and the savanna. Because the tropical rainforest and the savanna are alternative stable states, there's nothing between, and something happens, the rainforest becomes unstable, and it can flip into a savanna which is dominated by a fire. So this was work of a postdoc, Marina Hirota from Brazil, with us. And what is very nice, Simon Levin and I were in Sweden on a boat, and we were talking, saying, "Oh, what are you up to lately?" And Simon said, "Well, we have a paper in press in Science about the stability of the rainforest inferred from satellite images." I said, "Well, that's curious. We have the same." And they never told us, but they published our papers side to side. So you see, the time is ripe for an idea. We got 2 papers in Science in the same issue, and they were about this idea of how can you infer the resilience of this system from the data. And actually, we used the approach of Valerie Levina to infer the stability landscape. You see here, this is just computed directly from the data, and you see if there is a lot of rain, the rainforest is stable, as you might imagine. If there is very little rain, you'll have another stable state, which is the savanna, and there is a third one, which is the desert. But you can actually infer the stability of those different states. Like, this is the tree cover frequency distribution. This is the real forest. Okay, what's the probability of having forest as a function of the rainfall? And you can just directly infer that from data and make a map of the world picturing the resilience of the rainforest. So just as another example of this. Now I want to close off with asking how it all comes together, because it was one big illustration of the short span of attention, like jumping from one topic to the other. So how is it that we can think of ecosystems, of depression, of financial markets, the climate system, society, and find the same kinds of things? You wouldn't expect that. So in a sense, you intuitively say, "Wow, this is like perhaps a bit flaky, or it goes a bit too fast." On the other hand, there are fundamental principles that are so fundamental for dynamical systems that it doesn't really matter which dynamical system you have. If you put it up at a sufficiently abstract level, actually at critical points, some universal principles start to apply. Now, it may not be easy to discern those from the data, and it may be only in a few cases that we can really use them to tell something about changes in resilience, or ranking the resilience of different systems, of banks, of persons. But so look at it, whether the glass is half empty or half full. It is fascinating that there are those very fundamental things happening. And I think that this universality of some of those fundamental issues explain why Nobel laureate Ken Arrow, Robert May, others in this room that you've heard of, are addressing so many quite different systems. It's about the universalities. It's even though you would intuitively think, well, this is all very different and it's all very complex. Yeah, it's true. It is different. It is complex. But the glass is half full part of it is there are some very universal underlying principles, and sometimes they can help us to shape search images for things to look at. So sometimes when I'm in a particularly provocative mood, I call this Holism 2.0. That was when they asked me to give the annual speech for the anniversary of our university. I called it like this, and I call it like that because like holism has a pretty bad name, of course, in science, because it's very vague. On the other hand, science has diverted into very reductionistic small things that don't always help us to understand the big systems. And those universal principles can give us a handle to actually understand something about the complex systems. The work of Robert May helps us understand something about fundamental principles that may rule the resilience of financial networks, for instance. So it's not in many places that people are doing that. I think the Santa Fe Institute is one of the little revolutionary places that try to go viral, are aiming to go viral with their way of thinking, and as Chris Wood said, actually have a huge intellectual footprint, despite being a tiny little place in the desert, so to say. Here in Europe, we have a tiny little place in an orchard. Like a little network sparks the synergy program for the analysis of resilience and critical transitions. It's just an informal network of people meeting and talking about those similarities in financial, in psychiatric, in ecological systems. And then in South America, we have a similarly little kind of revolutionary thing we're setting up at the coast of Uruguay, the South American Institute for Resilience and Sustainability Studies, all with the same idea of bringing very unlikely combinations of thinkers together to think about these issues. And the basic problem, I think, much of us are addressing is the fragmentation of science. We know so much about the CO2 molecule. We know in very great detail some things, and that's beautiful. That's beautiful science. But we want to also understand the whole picture, and we don't get it from just studying the little bits and pieces. So we don't want to go to a holism that gives us a very vague picture. So the holism 2.0 is when we actually start to sharpen the image of the big picture, using the detailed information, but also trying to grasp those universal principles in ways that we can actually quantitatively underpin. So that's what I wanted to transmit to you.
Thank you, Martin. Terrific. I'm sure there are lots of questions for Martin. Yes.
Thank you, Martin. That was very interesting to speak. I found this kind of tipping point, kind of early warning system, concept very interesting in the context of financial system. Basically, we could add a lot of value to our clients if we could, get out of the market before next crash. Basically, well, I recognize the kind of universal common factors that the financial system linked to other systems. The difficulty for me is that, unfortunately, the financial system is slightly different. Essentially, this is kind of an example of hedge fund manager George Soros' view that reflexivity. So, i.e., how our understanding of the system, for example, in natural system, our understanding of the system doesn't affect how the system works. While in the financial system, it does. So, you look at your example of lake. You studied the tipping point. But the tipping point is a constant tipping point. That's it. But if in the financial system, if everybody had a view that SP 500 had a tipping point at 2000, then that tipping point would have moved because some would get out early. So I just want to try to get your views on how to tackle that kind of problem.
Yeah, that's a great point, and that's actually the reason that you'll hear me talk very little about financial systems. So I'm good friends with George Sugihara, who led the Deutsche Bank portfolio for many years, and I've been talking to Kars Hommes in the Netherlands, who is an advisor of the Dutch Central Bank, to Peter Nijkamp, who is another. I talk a lot. I hang out with economists and people interested in finance, so to say. Buzz Brock, William Brock in the US, and for that matter also Ken Arrow, and they all tell me like don't put your hands in the snake pit of financial because and so the first thing they tell me, well, the really interesting way the system is different is that anything you learn about the system will be learned, and so the people will use it, and that changes the system, and it leaves only this little tiny band of predictability that can be explored. And that's of course very, very true. On the other hand, there is also an elephant in the room, so to say, and I think that was shown in the talk of Bob May too. We are, and there was a question about that, like how rational are we? So one of the big issues driving these tremendously fast changes has just to do with confidence, and that's a psychological feature. So Cars Holmes in the Netherlands, working with the Dutch central bank, is doing those experiments with students in rooms that are trading, and of course part of the story is, can we predict, if you want, panic or inconfidence? So what do people do when they don't know what to do? Most people look at what somebody else does, right? So their behavior can become more correlated. So if you want, things can become more contagious. So I talked to Ken Arrow about that, and he thought it was actually quite sensible to think of it in that way. So, and I talked to George O'Hara about that, and he said, well, I cannot really tell you much because this is classified information, and the Deutsche Bank is paying me to do this. But he is interested in correlation between markets, and I would be interested in correlation between players. So it's one of the things that I think will be interesting to look at, to see whether you see more of a, if you want, like a mass hysteria effect. So do you see increasing correlation? Do you see people starting to look what others do? Of course, there's many more things happening, like people becoming adverse in risk. But so I would say that one of the things that might be interesting to explore is early indicators for like a group behavior and uncertainty of people. But again, I don't have a diploma for that. I can tell you everything about lakes. But if you would ask me from a systemic point of view, I think intuitively I would think that's interesting. We are actually looking into Twitter data worldwide now, as we are interested in finding early indicators for unrest in groups of society, and that's very much working along the same lines. So I would say there is probably a scope for some exploration in that.
Other questions? Please.
Can you talk about the difference between stable and static? Because I'm not sure whether, intuitively I would think that you could have a stable environment that's allowed to iterate and remain stable, but I feel that you're saying that if it's stable it has to be static, and therefore any iteration from there would be a movement of the ball. So I'm thinking of something like an economy where there's a massive misdistribution of wealth, or it's all concentrated, that if that environment allowed a greater distribution of wealth, and that would be a movement of the ball, but actually may just be prolonging the stable state and iterating and remaining a stable environment.
Well, yeah, you're opening a Pandora box if you ask what is stability and what is static. I mean, there's many ways to look at that. So nothing is ever static. Everything changes all the time. So when you talk about alternative stable states, that's like a theoretical construct. There is not such a thing as something being static. So you should really talk about like dynamical regimes and alternative dynamical regimes, and whether you might move from one to the other. Now, then the concept of how should you look at internal change for that, it's an interesting question. There is this group of people thinking about resilience, and they say, well, okay, resilience of what? Resilience of civilization, of having a wealthy society. So what does that mean? That means actually the need for the capacity to change. Because like if we don't change, we keep doing things the same way, actually, in the end, we become maladaptive and the system becomes fragile and it crashes. So actually one characteristic in that view of resilience, if you want, stability, is actually change, and it's more adaptive capacity. It's the capacity to realize that you fundamentally need to change your system, or else it'll go more fragile, more fragile, more fragile. In the end, it will crash.
Louise and Mark, before Ole, who's next, let me push on that same question a little farther. Much of your talk has assumed that there are multiple stable states. Many of your diagrams show two, with rapid transitions in between. Let's take the financial crisis of last decade. What if, instead of that being, as many of us think, a transition between two different stable states that we didn't anticipate, what if the normal state includes such transitions, and there is no way to model them away, there is no way to analyze them away with early warning signal analysis, because they are simply part of the underlying single dynamic that we have.
Yeah, that's a very good point, and of course, like there's many systems that have those intrinsic boom and bust cycles. Like one of the famous one is forest fires that naturally always occurred in different systems, including in the boreal forest and in the savanna and the rainforest. It's the way it is. Something builds up, it builds up, and it all crashes. And you'll have small crashes and you'll have big crashes. There is this parallel distribution of the size of events that will happen, and it's part of the dynamics of the system. That's how it works. In the case of the tropical forest and the savanna, actually there's two attractors. One is the tropical forest that has no fires, and the other is the savanna that has this intrinsic dynamics of small and large crises that actually keep the landscape open. Now, if the conditions change as the climate gets drier, actually the tropical forest occasionally becomes burnable, and then you can have mega fires that actually eat up huge amounts of the tropical forest. So it is definitely true that intrinsic in how the system is, it can contain the recipe for a series of large and small shocks. So that's very much the case. And when I saw the picture of the last picture that was, according to Robert May, more important than the whole rest of the time series, you see this like for a long time nothing happens, and then actually something happens in the 70s. You get on a different trajectory, and that is a change. That is a change in the system. We went to a fundamentally new situation. That is maybe a situation with a particular kind of intrinsic instability.
Thank you. Ole.
So thank you, Martin, and thank you, Chris, for somewhat preempting my question. Actually, Chris and I were emailing before this meeting, and I think we raised something similar. So my comment or question, or part of the reason I'm here, was that I was interested in what you had to say about the climate system and transitions there, and I'm now actually not quite sure what you said. I understand that there are different stable states in the climate system, but the question whether you can see them, whether you can see transitions happening or anticipate transitions happening before they happen, really depends on the mechanism whereby they happen. So if the pictures that you've shown, if they are correct, if they reflect what is going on, then it's something where you have a gradual process that somehow changes the stability landscape slowly, and at some point a transition happens. But you can imagine a different scenario where, for instance, the planet is hit by a meteorite. There should be no early warning signal. And so by doing this analysis of looking at the fluctuations that you see as you approach a transition, you could sort out the question whether this was a meteorite strike or some volcanic eruption or something like that, or indeed, if it's more in line with the picture that you showed of the slowly changing conditions of the stability landscape, can you comment on that? Which one is it, or in how many cases did you look at several of these transitions in the climate system, and what did you find?
Well, first of all, the person to really answer that question, and he will, and you say you'll have a lot of opportunity to talk to him, is Tim Lenton. I mean, he is the expert in this room on that. So I can comment briefly because unfortunately I have to leave for the annual outing of our graduate students just at lunch. But so several things about about this. First of all, it can be both. Like the dinosaurs disappeared when a meteor hit the Earth, but there is indications that actually the whole biota on Earth had come to a point of fragility, and that actually that meteor was maybe not just the fly sitting on the chair, because it was a pretty heavy fly, but it's often a combination. It's often a combination. And then when you look at those climate pictures, you see the time scale on, like the first one I showed, was many millions of years. So, and we have evidence that in the climate system there's like things such as continental drift, volcanism, things that change slowly, that put a stress on the system, and then every once in a while flip you into an alternative state. It can also be that, as Tim can tell you, that it was a new invention, like photosynthesis, that put you on a different trajectory, and we went to an Earth with oxygen in the climate. But of the examples I showed you, the end of ice ages and those transitions, it looks like something was gradually building up in the Earth, and then it flipped. Now, when you want to think of the current situation, then it becomes: are we gradually building something up, or are we more like a meteor hitting the climate system? Because we're changing a lot within 1 century, and actually the typical timescales of this climate regulation systems are much slower. So it's not like we are very slowly changing the stability landscapes. At least if you look at the slower parts of the climate system, such as ocean currents and ice sheets, if you look at the atmospheric part, it's different, because the time scale of the atmospheric part is much faster. Like the build-up of monsoon and crash of monsoon systems and circulation patterns can be pretty quick. So it depends a bit which part you're looking at. But I'll just prefer to leave that for Tim, because he is the best person in the world really to talk about that.
Please join me in thanking Marten one more time.